Imagine to fight Alzheimer, you have built a high-tech sensor box containing a PCB with an FPGA, a cage for an optical module, which you buy from a third party, and a PCB layout done according to your company's best practices. You test it, and everything works out the box straight away. But after 5 years, this module goes obsolete. You plug in another from another manufacturer, and all of a sudden, 20% of failure in production. And another 10% in the customer field. Nightmare. So now, the question is, where does the problem come from? The digital part was already tested in other projects, so it's not very probable. But there is this layout, there is this PCB manufacturing process, and there's of course this module. It must be somewhere in the analog part, must be something with signal integrity, but where is it? So an expensive witch hunt panic starts. I did not make this case up. Signal integrity is real, and it is hard. Who already encountered signal integrity questions in their projects? Okay, not for nothing. How to avoid this kind of mess-ups, at what cost, and how to effectively combine measurement and simulation. My name is Sjoerd Op, and in the next 30 minutes, I will take you along in Technolution's pilgrimage. And you will receive practical signal integrity tools for measurement and simulation to use measurement and simulation and optimize the return on investment to make great products. But first, let me tell you a story about how signal integrity can keep you awake at night. 2 years ago, I grew convinced that we needed adequate measurement equipment, a 44 gigahertz vector network analyzer. Now I only had to convince our management. So we rented one to try for 10,000 euros a week, and I bought a set of test cables with it. And at this staged photo, we look all very happy and serene, but it didn't start out that way. Because one of the test cables I bought, in combination with the calibration kit, sometimes had intermittent problems. And of course, the question was, is the problem with the calibration kit, which we rented, or with the cables, which I bought? We had no idea. And this would determine who would pay the 40,000 euro bill for the next 4 weeks we needed to find out where the problem lay. You can imagine that I didn't sleep too well. And for weeks we did not have any clue where the problem lay. Until one morning when I looked into the connectors and I was wondering, could there be a mismatch between the outer diameter of the male pin and the inner diameter of the female contact? And if so, which one fails to comply with the specification? And for every day during those nerve-wracking 4 weeks, the stakes were rising. We'll see how the story continues later on. But first, let me introduce Technolution. Meet Martin, one of our die-hard gamers, together with another gamer in his spare time, got the idea of creating a digital twin for our tunnel control systems. And now it grew to be a core part of the operator emergency training we develop. This is a super fancy atomic force microscope for chip manufacturing. And we helped our customer all the way from system architecture, GUI, FPGA development down to physical modeling and analog front end. And we guided them through new product introduction, lifecycle management, supply chain management, international certification. In short, everything to make their product a success. And now we come closer to today's topic. This is a multi-beam scanning electron microscope, and this is a tiny part of a mouse brain. And the microscope can scan it at 10 nanometer voxel resolution, producing 320 terabytes of data in a few days. You can imagine that with high-speed digital signals and very sensitive analog signals so close together, because amongst others, we developed all the electronics, you need deep understanding of signal integrity. And we had the feeling we were not yet having this deep understanding. So we devised a master plan. Clearly, we would need some combination of simulation and measurement. And to connect the two, we would want to try a real example of a breadboarding PCB with a link on it, which would then be exercised by an FPGA. An FPGA which could also measure analog eye patterns on chip, so that we really know what the signal looks like according to silicon. And of course, we would like to see a perfect match between simulation and measurement, and maybe in practice it's also helpful to build this match bottom up. So we also put individual structures, just one via, just one trace, also on a PCB, in order to measure it with the vector network analyzer. In case you didn't hear and understand it already today, it's just this yellow ohm meter which can measure impedance over the course of time, just a tiny bit more expensive. It can also measure a lot of other things, but we're now using it as a TDR. And so we did. So we created PCBs with 200 test structures. We bought this then Xilinx FPGA board, and we started to measure. Now, in general, if you are measuring, to measure properly, you need a fixture. But to cancel the effect of the fixture, you need to calibrate according to a standard, in this case, an empty ball. And by subtracting both, you isolate the interesting device under test. Now, in our case, to measure properly, you need fixtures. And to cancel the effect of the fixtures, you need to calibrate with one or more standards. And by subtracting the two, you isolate the interesting duty. Now, in general, there are a lot of different calibration algorithms. You get nothing for nothing. If you want more accuracy, you need more effort. So these are some classical calibration methods. In encircled, you see the number of standards measurements that you need, and each standard means space on a PCB, it means effort to lay out it, cost for the components. We got acquainted with a relatively young exception. It's called automatic fixture removal, which also needs just one standard, one reflection or one through, but still has quite a good accuracy. It needs, I must admit, some fingerspitzengefühl, but once you have it, it's a real time and space saver. But even with one standard, these standards occupy quite some PCB space. You need to think of it beforehand, and in practice, you may start measuring, or maybe a customer will come to us, we have a problem, and now we want you to measure. So you didn't think of standards beforehand. Wouldn't it be nice if we could probe on a bare board, for example? Well, let's first have a look at what's possible with probing. So what we have on the lab bench here, and Marcel will show you, I need to switch here, is one of the test PCBs, and we are now looking at a 100 ohm microstrip trace with dedicated probe landing pads on both ends. And here in the top left, we see the TDR plot. So you see the blue curve, which is the impedance as function of the time, which maps nicely to the place. And where the curve goes up here is the time that corresponds to the probe tips. So could you please land the probe? Nee, nog niet. Eerst moet de probe naar beneden, denk ik. So you see we're starting to touch down. And now we see this strange transition region, and then something which ramps up slowly from 95 to about 100 ohms. Okay, maybe correct, something that we try to design. Why do we have this slope? Because in layout it's perfectly the same along the length. I don't know, but maybe if you have some experience with TDR, you know that slopes can be indicative of loss. So nothing very surprising yet. At the other end of the trace, there's also a probe, which we already landed. But before we show the result, I was wondering, what do you think the trace will look like? So for your information, the setup is perfectly symmetrical. The layout is the same. It's just a straight trace. A probe landed on the left and at the right. Everything is the same seen from the left or from the right. Will we obtain the same curve seen from the other side? Who thinks we will obtain more or less the same curve?
The reverse.
Why would you expect to see the reverse?
You go from A to B, so the left is A, right is B. Now you go in reverse. You go from B to A.
Yes. So yes. So if let me translate and interpret a little bit. Your hypothesis is if this trace, this slope, has not something to do with the loss, but really with some material parameter or something that gradually changes from the left to the right, then if we see it from the other side, it should be mirrored. Okay, possible. So the important point to remember here, interpretation of TDR plots is not as straightforward as it looks, because what you see, this impedance here, is when looking through the same transmission line that you try to characterize. So loss, for example, generates a slope. Okay, but I think it was too easy to understand that there was a catch somewhere. Nobody dared to say it's the same. Let's see, Marcel. Yes, please. And indeed, it's mirrored. But now the loss story, at least, is not a complete story. Anyone has an idea what could explain this change? Because the layout is perfectly symmetric.
Maybe the height.
PCB height, okay, interesting. Maybe the pressing is not equal. Possible. Other hypotheses?
Like pressure difference from the top?
Pressure difference, that I would expect to see here at the beginning, because both this, it's maybe a bit strange to interpret, but T0 corresponds with both ends of the trace.
Weaving directions.
Sorry?
Weaving directions.
Weaving directions, yes. That's also what I suspect. But it cannot be the whole story, so I was also asking the question because I really wanted to know the answer. Weave. So the PCB, this is FR4 IS400 substrate, is an epoxy with glass fiber fabric in it. And these glass fiber strands have a different dielectric constant than the epoxy in between. So if a trace is running just above it or just not above it, the characteristic impedance will change a bit. Okay. This is part of the story, we are sure. And it's not a complete story. We are also sure of that. So it's also under investigation. Okay, but this was probing still with a dedicated probe landing pad. So it means you had to think about it beforehand. What if you have a bare board with a problem with, this is about 10 centimeters of trace, a bit of strip line, a differential via, trace, 2 45-degree bends at an outer layer, something like that. Can you probe and draw meaningful conclusions? And to know it, we duplicated this and we fitted it with a coaxial fixture. So that's our reference truth. And we also put some more real life connections to it. So here, this is a BGA field with 2 adjacent pads. And this is these are rectangular pads for example, board-to-board connector. And to make it a bit harder, probes often come with a certain pinning. For example, ground, signal, signal, ground, or ground, signal, ground, signal, ground. That's very nice if your ball out, your BGA ball out perfectly matches that, but in practice it doesn't. Fortunately, there are also probes who do not have a galvanic ground contact, so just signal, signal, that's it. Well, often the pins of interest or the balls of interest are just next to each other, so you can often use this probe, but you only have a capacitively not so well-defined ground contact, so clearly you cannot perform common mode measurements, but maybe it's still good enough to draw useful conclusions. That was our question. So here are the results. Our reference truth in blue. So what you can see is that the strip line part is more like 116 ohms or something, which is not what we ordered. So there's a problem. And then there's the via, and after that about 100 ohms. If you look carefully, you can even recognize the 45-degree bends as small bumps here. And now we're going to look at the in situ probing. Now, here you see some deviation, but the 116 ohm problem is clearly identified. So the point I wanted to make here is, yes, it's not ideal in a sense, but it is ideal in the sense that you do not need to think about this beforehand. That is possible. Now we know how to measure. Let's make the link with simulation. Most obvious use of simulation would be to verify your models, because before making simulation of a whole complex system, you are using maybe models coming from manufacturers for connectors or other components. You need to know if they are trustworthy. So for that, you need fixtures like these. A slightly more advanced use of simulation is model extraction. So for example, PCB material, there is a datasheet with specifications. The problem is that there are many different ways of measuring PCB properties, and some methods are better in repeatability and some methods are better in realism, in the sense of electromagnetic physics. And the manufacturer is interested in a repeatable process. So they use the kind of measurement technique that gives you a consistent result, but not necessarily useful or good enough for electromagnetic simulations. So to see to what extent it was a real problem, we put, thank you, Nick, this BT structures on our test PCB. So it's just 50 ohm trace with a slightly thicker trace and then 50 ohms again. And then we started to backfit. The idea is that in simulation, you simulate what the behavior should be like if the manufacturer's parameters were correct, and then you're going to tune those parameters in order to optimize the match between simulation and measurement. And then you say you have extracted those parameters. So here in red, you see the simulation, in blue, the measurements. We're first going to look at the delay, because that's indicative of the dielectric constant. And I can tune the dielectric constant in order for these curves to approach quite nicely. Then we have the pressing height variation and also over and under etching, which both have a quite subtly different signature in the TDR plot. So we can tune for them to match nicely. Of course, I cannot get this to work as fast as artificial intelligence, and especially not under stress. And finally, we can have a look at the loss. So that's the upper right corner. Tune tangent delta to match more or less. This way we have extracted the parameters for one layer. We can repeat the exercise for example, 2 layers or 3, and that way get a more trustworthy model of the substrate. Okay, this is a very nice set of parameters, but it's true at room temperature. What about temperature? So we put it in the climate chamber, we heated up the trace locally, and we saw, for example, I think Jens also showed it, a non-negligible loss change as function of temperature. But it's great to have these kind of numbers, because then you know what margin to include in your design phase. This is something you cannot always prove in measurement. You can be lucky and have a pass because your silicon was more permissive than required, and then still have failure in the field because that silicon still compliant with the specification, but you just didn't include sufficient margin for temperature. Okay, all this very nice to have this temperature dependent substrate model, but it was also quite an amount of work. So this model comes with a price tag. And the question is, when is this worth it? And let me now give you tools to answer that question. And for that, we need to completely zoom out. So if we go from idea to production of a certain product, please take in mind your main project, currently the main product that you're working on. And let's use our arm as an indicator. Who is more at the Idea side, point to the left. If you're more in the production phase, to the right, or something in between. Let's see where we are. Everyone raise an arm. Okay. Interesting poll. I see quite some at the left side, also quite some at the right, not so much in the middle. Interesting to note. You probably have seen those curves before. In the beginning, you do not know a lot about the product yet. Hard to take decisions, but you have a lot of freedom. And towards the end, it becomes much harder to make change, also more costly. And this is true for all kinds of concerns, not only signal integrity. And experts of all those cross-cutting concerns will offer you the same solution to this problem that changes become expensive in the end. They will say, well, talk with me at the beginning and listen to me and keep me on board all the way, and you will not have costly surprises at the end. So for EMC, thermal, design for manufacturability, user experience, even sales. But I think there's a problem with this advice. Because if you put all those experts around the table, at best, it becomes a very expensive experiment. And at worst, the creative process comes to a grinding halt. So what's the solution to this problem? What I would like to suggest is to have proportional doses of attention, in this case for signal integrity, along the way. So for example, in the idea phase, it's perfectly fine if just your team watches a 30-minute awareness video on signal integrity and asks themselves the question, are we concerned? That's enough. A little bit later, when the architecture becomes more clear, you can do a 48-hour scan, quick scan, with some numbers to discern where the big risks lie. And also, as Jack pointed out, to look a bit broader and see the connection with EMC, power integrity. And also to plan ahead and say, okay, given these risks, what are the wise next moments? And at those moments, how much attention should we pay in what manner? That will different for every product. Okay, I said we need both simulation and measurement. That's an interesting debate. We already had it around coffee. Some say we should completely rely on simulation. I think you really need both because in the end, the proof of the pudding is in the eating. And simulation can tell you everything, but has only something to do with reality if you have taken the dominant effects into account correctly. And maybe you do not need to do it always, but it's always wise to check sometimes whether your simulation, your conception of the world, has something to do with reality. But there is a particular challenge with simulation. Because models are so malleable, the temptation is to always improve them. They can always be better, they can always be more close to reality. When to stop? In other words, how to get a positive return on modeling effort. Let me illustrate our approach with a real-life example. For Amsterdam Scientific Instruments, we had to verify a layout for a scientific camera, which consists of a large array of sensor chips, PGA soldered on a PCB in vacuum, with a large as possible active area and necessarily some blind spots where those signals traverse the silicon from front to back. They are very tiny through silicon vias, so at the top it looks a bit like this is a row of through silicon, maybe 60 or something through silicon vias, and this is the size of a VGA ball. And you can see that the fan-out structure in this redistribution layer, which is the bottom part, is very strange. It doesn't comply with any rule of thumb for signal integrity or power integrity for that part, and you also need enough pads for thermal conduction because in vacuum the heat needs to go somewhere. So you can imagine that this is a complicated trade-off. And the stakes were high because producing this redistribution layer at the back of the chips takes about 2 months of elapsed time. So if there would be an error there, it would be really costly for the product. Return on modeling effort. This question comes back in I think every product. When is good enough? Refine models or stick with them, perform external compliance testing or belief simulations. And this is the tension between quality and cost. And I think it often occurs a bit like this. So you are the managers, and you're pulling towards finishing the project. As to be fair, there must be 3 persons pulling at the other side. So, okay. We need to start out here, otherwise it's not fair. And I suggest you stand, because otherwise, well, if you want to win. Okay. So the question is, the question is, are we going? Yeah. Oh, okay. Already injured. Maybe you Jens, you can help at the other side. I'm sure you have management ambitions. Okay. So you're already pulling. I didn't even ask a question. So the question is, are we going to perform more simulations or stop simulating? 1, 2, 3, pull. Excellent. Okay, thank you. Okay, so what was this? What was this like? How did you experience it? Did you like it?
That's not reality.
Why isn't it reality?
In reality, then the managers are of course.
Oh, in reality, yeah.
So hey, what does it cost? Is the first question.
Yeah.
Second question, how much time does it cost?
Yeah.
What does it bring? What's the return on investment?
Yeah.
So this is the first time to bring.
So you recognize the tension, or
Yeah, that's one more thing.
Yeah.
Of course, nothing is free. So.
Yeah, exactly. And the business need to run. Okay, understood. I think this is more intensive than it needs to be. And I think the reason is that the people are opposing each other. And I think the solution would be, instead of being faced to each other, to be standing next to each other, opposite of a third subject. And my suggestion is, this is the return on modeling effort. So with each choice, because there are numerous choices like these along the way, you can openly discuss what the expected improvement is. I will give a tool for that later on, and what your estimate is of the modeling effort. That needs to be based on experience, of course. It's also important to note that the required effort depends a lot on your starting point. Just to give an example, this vector network analyzer and knowing how to use it costs in the hundreds of thousands euros range. And similarly for simulation tools. But for example, for simulation, once you have models and you have run first optimizations, solving a similar problem another time, using those earlier cases as a template, you can repeat it for much lower cost. So this is one consideration you need to take into account if you also have to decide of doing something yourself or outsourcing it. And I think if you look at it this way, and this is a complicated exercise, but it becomes more like a balancing act. Let's have a try for that one. So now we have only place for 4 people, so 2 managers and 2 engineers. No, for fair comparison, it needs to be from the same pool. So so it's a labyrinth. The goal is to solve it, and we start where there's some start. I don't know where the start is. Okay. So I think you should put your feet on the same colored footprints. I think we're missing one manager. Yeah. But sorry, you need to stand on it with both feet. That's the difficult part. You need to go all in. Yes. Now while they're working, I make some interesting observations. They were intuitively holding each other. This is different than pulling the string. And they also recognize that it's a series of choices and you do not know what the next choice will be, but you can focus on the next choice That's language for you.
Too fast, people. You-
Great.
Okay, now we go.
And they are getting fanatic about it. Thank you. Thank you very much.
Probably also going well on the bachelor parties, I think.
Yes.
Team building,
Team building and so on.
with beer. Problem solved? Okay.
So the case of the redistribution layer I told about, we had weekly stand-ups, and at the beginning we thought the biggest problem would be signal integrity, but actually after 2 iterations we found out that will not be a problem at all, and that way we could focus on power integrity instead and finish the investigation within budget and draw conclusions of which we were sufficiently certain. I'm going to skip this due to time. Now, did you still worry about this case? I did.
I think some of the has still turned on a normal SMA connector on the.
You think someone connected the normal SMA connector
Yeah,
to this?
Then you do really destroy.
And okay, interesting. And in which way do you destroy it then?
Because the dimension size of the SMA connector pin is not well defined.
Not well defined.
Compared to 2.9 or 2.4.
And in what way will you damage the female connector, for example? Yeah, you will bend open the spring pins. No, fortunately Guido had this amount of experience. I didn't. So we.
So now we know who did it.
Oh, you're also ready with him.
I reserve a precious place and help people to do that.
All you needed was a wrench to tighten it.
Yeah, but just a tiny bit. The orders of tens of micrometers. That's not so easy. We developed a method to calibrate our microscope and to also determine its measurement uncertainty because there were some stakes. And the conclusion was that our connector was in spec and the rented one wasn't. So saved by the bell.
You never know when you have rented equipment, right?
Yes, that's another cost aspect when you have to decide between in or outsourcing. But we also learned a lesson, and that is that connector geometry is serious business, but because it could as well have been our too cheap cable or whatever. So we bought ourselves this connector gauge, hoping to avoid this kind of adventures in there. So we have looked at modern measurement and simulation techniques. We have looked at return on modeling effort, and I'm now going to offer you one last tool. Because when architecting a system, sorry, yes,
Just a
Daniel.
question,
Yep.
just for the before one. This one was your own, not the gauge box, was your only the depth.
Protrusion. Excellent remark. It does not measure the diameter. Our hope, but because it was a rental, we had to return it and we'll not get it back easily. Not exactly this one, and maybe not exactly in the same state. Our hope is that protrusion measurements would also have revealed this problem, but we will never know. Still, we are interested in developing an optical measurement system for other connector geometry issues. So if there are partners here interested in collaborating on that, we are interested.
Spare channels or something?
No, nothing spare. No, it was already quite expensive to have everything one. But it's a good remark, Xavier. This last tool is meant to keep the overview and to put the focus at the right place. So over the course of the last years, we made an inventory of 22 contributors, as we call them, that positively or negatively contribute to signal integrity. And depending on your system, they may or may not apply all, but just give it to you as a kind of checklist. So coarsely, we have signal processing, different kinds of equalization amongst other cross-cutting concerns like the stack-up, and then all kinds of elements which should be considered large or small, of course, depending on the rise length. So that may differ in your case. Okay, that's nice. but it's still a bit daunting, this big list. Where should you put I think for every item you could do a PhD just on that topic. And that's not possible in every project. So how do you put the focus at the right place? And fortunately, we're not the first to ask ourselves this question. So the IEEE Ethernet Working Group has thought up the channel operating margin, which is a single number metric, a bit like kilograms of CO2. It's not true, but it's useful to make decisions. And it's simply in the eye diagram, the ratio between the eye opening and the crosstalk and noise. And this then is, of course, as we should expect, a very complicated calculation based on the contributors we just saw, but at least there's a contiguous path from those contributors we just saw all the way until the goodness of our signal. And that way you can weigh what are the more and the less important contributors. And this can be done pre-layout, but also based on measurements, for example. And if you think back of the return on modeling effort, this is something that can be used for the enumerator to estimate the improvement if you're working on this or that contributor. Let's wrap up. Remember the sensor box we started out with? We now have the tools to diagnose and even avoid this kind of signal integrity mess-ups. Use modern measurement and simulation techniques, keep openly and continuously discussing the return on modeling effort, and put the focus at the right place. Remember Technolution's passion I showed at the beginning? We love the challenge of combining complex technologies into a working product. And as I showed, we master the tools to make high-speed work. And if we can combine this with our other competences, other expertise in your project, come to us and let's make great products together. Thank you.